Thank you very much, Dr. Xiaopeng Xiao. Oh, sorry, Dr. Xipeng Xiao. I'm sorry. Thank you very much. Okay. We'll skip the questions because we missed a bit of minutes at the beginning. Next speaker is Mustapha Assawi, who is going to speak about SRv6 behavior optimizations. Mustapha is a product manager in the service router project group of IP Networks division at Nokia. He holds an electrical engineering diploma from Polytechnic School of Alger and an MASc in electrical engineering from the University of Ottawa. Mustapha Assawi has been in the product management role since 2004 and is responsible for the MPLS and segment routing features in the SRv6-based routers. He is also the lead PLM for the SRv6-based PCEP and other SDN features in the NSP PC controller. Finally, Mustapha is an active participant of the ITF MPLS, PCE, and Spring working groups, and is a co-author and major contributor to many drafts in this working group. Welcome, Mustapha.
Thank you,
Back to you,
Bruno.
I can switch to your presentation.
Excellent.
Okay, it works. Up to you.
Thank you. Good afternoon. What I'm going to talk about is a few cases of SRv6 behavior optimization that I wanted to kind of bring up. And also, I completed the presentation with a number of best practices to deploy SRv6. This is the outline, so we'll go through each of these items now. First of all, so obviously we know SRv6 requires some complex packet processing, whether at the ingress PE or at the transit P router or at the egress PE. In some cases, data path must combine multiple behaviors, of course. For example, you can terminate a node SID, so that's an AND behavior, and then you have to push a TI LFA segment list using an h.insert_read behavior. Another example would be to terminate a binding SID, expand the segment list using, for example, the end.bsex.incaps.read behavior, and then push a TI LFA segment list using the h.insert_read behavior. So these behaviors, of course, they have to happen. They have to happen at the same time. When TI LFA needs to be activated, the backup path needs to be activated. You need to have both behaviors in parallel. So that combined behavior is not actually described properly in the network programming draft or in the NetPGM extension insertion draft. So in some cases, data path could optimize a combined behavior compared to two separate behaviors, of course. So that's obviously implementation specific, but it's that optimization could be done. And these kind of optimizations apply to both base SID or compressed SID, so it's kind of the similar issues. So the first case, and I apologize for the busy slide, that the only way you can explain some of this is actually to show the packet flow through the network. But basically, what the case here is, we're pushing a segment list using basically h.incaps_read here at the ingress PE, like node 0, which has basically two SIDs in the segment list. Like the first one is basically a node SID of node 2, and then the second one is actually the destination node SID, which is node 4 here. And then there's a service SID, which is an IPv4 IPVPN SID or end.dt4 behavior that's also configured here on the destination PE. So when the packet arrives at node 2, so you can see the encapsulation here has basically in the destination address field in the outer IPv6 header, there's of course the first SID, which is the node SID of node 2. And then the other two SIDs go into obviously the segment routing header. But when we hit node 2, then we terminate its node SID, which is in the DA here. And the packet output basically will do basically an AND behavior with PSP. And in this case, of course, the segment left is 1. So but if we go on the primary path directly to node 4, the packet will look like this. So we update the DA to the next SID, which is the node SID of 4, and then we decrement the segment left. But if we go via the backup path, assuming node 3 is acting as a PQ node, then you can see that we have to insert a second SRH that contains basically the node SID that we moved out from, which was supposed to be in DA. We move it now into an SRH of the TI LFA SRH, actually, for that matter. And then basically the original SID, this one goes into this new SRH. So this behavior, so we have to do these, like for primary path, there's only one behavior, but on the backup path, we've got a combined behavior. So now the packet drives on node 4, whether it comes directly from node 2 on the primary path or on the TI LFA backup path, it actually looks the same. And node 4 doesn't end PSP behavior. So this behavior done by node 2 is actually on the backup path, is actually a combination of two behaviors. And it's important that we could optimize these obviously behaviors in data path. The other addition to that previous case is, well, you notice that the segment list we had here for the SRv6 policy on the ingress PE had a node SID. The last SID was a node SID of node 4, which actually comes from the same locator as the service SID. So here the underlay and overlay are using the same basically locator, which is a good thing because then we could actually optimize further the segment list here on ingress, and we could actually suppress the node SID of node 4 because the service SID, which comes from the same locator, is sufficient to give us reachability to the destination node. So that's actually good news. Now, how do we do that? Like there are two ways you could do that. One of them is obviously if let's say this segment routing policy was advertised in BGP and we got the structure sub TLV, which gives us the locator size and information, then we can compare obviously the size of the locator for this SID with that of the service SID, which is advertised by IGP, let's say ISIS. And then we can compare the bits that are part of the locator, and then if they are the same, then we can say we can suppress the node SID and keep only service SID. But otherwise, these are kind of, at least for the BGP SRv6 policy, it's an optional information. So if you know that the entire network uses the same size locator, then the other thing you can do is you make the assumption that, yeah, I can actually safely compare the first, most significant bits up to the size of the locator, which is assuming common in all the network. And that way you can also skip. So these are kind of the two options you can have. But then the processing becomes much simpler, as you can see, like the packet that drives to node 4 is actually much simpler, and it's much less processing than in the previous case. Now, let's talk a little bit about OAM and SBFD packets, because while we can talk about user packets, but OAM is important as well. So what are we trying to achieve here with OAM or with SBFD? So first of all, we want, say, do a ping or trace route of a prefix or a SID of the endpoint via the SRv6 policy. So that's one thing. And the second thing is we want to check the data path continuity of that SRv6 policy segment list with SBFD. So what is the issue? So the issue is if the last SID is terminated at the midpoint node, if the last SID of the SRv6 policy is terminated at the midpoint node. Remember, here we don't have a service SID because this is really an OAM packet, so there's no service SID that is the last one we add into the segment list. But if the last SID in the SRv6 policy is terminates at the midpoint, that OAM or SBFD packet will get extracted into the control processor for further processing. So we don't want that, right? For instance, if the last SID is a B SID or an adjacency SID, definitely that packet gets extracted, and we're going to look at high layer processing at that midpoint. But that OAM packet may not have been destined to that midpoint. So that's the issue. So what are the possible solutions? Well, first of all, for ping and trace route, we don't have an issue because you're always pinging a SID or a locator or something. So there's always an additional address that you add to the segment list. So there's no issues there. For SBFD, you can choose to add an additional IPv6 address of the endpoint or a SID of the endpoint. We can look back into defining OAM and SID. I don't know if you remember, but originally in the SRv6 OAM draft, there was a definition of an end.op SID, which was supposed to be an OAM. That was removed. Of course, it wasn't needed initially, but in this case, for SRv6 policy, we may need something like that, so that's another option. And of course, you can always suppress the last SID of the SRv6 policy, as per the previous example. If that additional SID you're pushing and the last SID are coming from the same, you can always suppress. So let's illustrate this quickly here. So if we send the SBFD packet in a UDP encapsulation, and our SRv6 policy basically had the last SID, the only SID actually on the segment list is a binding SID that is instantiated on node 2. And that binding SID is using an AND B6 encap read behavior, and is pushing basically a couple of segments here, like node 3 and node 4, basically. If that packet arrives to node 2, as you can see here, it's going to arrive, in this case, it arrives without even an SRH because we're using the reduced format of the SRH. But even if it comes with a segment left equals 0 in the SRH, this router will send it to the control processor. And obviously, if it's an SBFD packet, it's not going to be processed because your discriminator value is not going to match his local definition for that as a reflector for SBFD packet. So we wanted the packet to go all the way. So now, if we insert the additional SID, so if we insert this additional SID, whether it's an address or in case of ping and trace route, it's obviously you're pinging something, an address. But if it's SBFD, you could use a special SID or another IPv6 address. Then the behavior will be correct because we hit this node, and then what we do is we push the additional IPv6 header for the SRv6 policy, for the binding SID, and the packet will make it all the way to the destination, and we'll be able to process it. So that's really the intent of doing this. So that's really a solution to do this in the case of SBFD packets. The next part of the second part of the presentation, I wanted to talk about some of the best practices for SRv6 deployments that we've kind of been working with a number of our customers. And every customer has their own specific, obviously, environment, operating system, et cetera. So I mean, these are really things where it's kind of almost like a toolkit where you can take the things that make sense to you. But basically, in terms of address locator and function assignment, so obviously, we know that depending on the number of nodes you have to cover in that SRv6 domain, you can use a /32, /40, or /48 for the locator block. And you can assign them per network, per area domain, per slice. So it depends on the use case. You can have a very wide or large network, or you can have separate locators used in different parts of the network. So the locator block can be assigned from unique local addresses if it's a closed network or a private network, or it can be taken from the global unicast address space. You can structure the locator in a very creative ways to help basically to ease network identification and troubleshooting. For instance, you could have the locator could be subdivided into network ID and node. Of course, it is subdivided into network ID, and of course, there's always a node ID for sure. But you can have a node ID, can contain information such as host ID, zone area ID, flexible algorithm number, slice ID. So it's really, you can be creative in how you structure this information so it's meaningful to you. The function feed could be like a service ID, could be a CNF, VNF ID, could be a tenant ID. So that's really the kind of ideas you can think about, because this is all the things you have to do ahead of time before you start the deployment. And once you deploy, then basically this is ready to be used. It's easy to troubleshoot, etc. We know that you can use, obviously, functions of size 20, 16, 20, 32. For example, these are typical values that we see in implementations. 20-bit is actually a nice sweet spot because it achieves the same scaling as MPLS services, for instance. And also, it allows to do what we do, the function or transposition of the function of the SID into the label feed of the NLRI for the VPN routes. It allows us to do optimize route packing, especially for EVP and VPWS services. You can also define static functions. So while the prefix is configured and we know what it is for a specific algorithm, you can actually use static functions for each of your VPN IDs or slice ID or VNF, CNF ID. And that's actually nice because You could even reuse those static functions because the locator being unique to each router, a specific entity can be, for instance, if you have a dual-homed service or function or application or CNF, VNF, then you could use that same function on two routers. But those are two routers or two access leaf, let's say, have different, obviously, locators. So it's easier to, like you can easily, they don't get confused, right? Yeah, and then of course you can do prefix summarization to reduce the number of IPv6 prefixes advertised between areas and domains. Also, the other thing is when you are in a multi-area, multi-domain, then obviously you can have a base network slice for best effort services, and then you can assign color-aware network slices or intent-aware, whatever you want to call them, using IGP Flex Algo, and each of them will have its own, obviously, SLA, parameters, and will have its own locator. And then, of course, you can leverage IPv6 summarization. Regardless of the algorithm, you can do that in both the base and the Flex Algo algorithms. In terms of the migration, you can migrate and do it PE by PE by introducing SRv6 smoothly into the network. I've got an example coming in the next slide. And then you can also use a gateway between an MPLS and an SRv6 domain such that you don't have to have SRv6 end-to-end to deploy it and take advantage of it. So that helps you do that, and we've got a couple of examples for that. So for instance, if you are deploying a telco or in this case telco cloud data center or mobile edge data center, that's IPv6 only. You can use SRv6 for VPN services for tenants as well. And so if you introduce SRv6 here, then you can still keep your investment in your backhaul network, as with MPLS, and have the gateway function that allows you to convert from MPLS to SRv6. So this is actually very nice. You can, obviously, by introducing a VRF here at the boundary, you can also take advantage of scale. You can summarize routes. You can inject default routes. You can summarize routes. So that's actually an advantage as well. And you can see the nice thing is that as the routes are being advertised from one domain to the other domain, some of the attributes are being passed. Like, for example, the color extended community attribute can be passed such that you've got a consistent definition of, let's say, Flex Algo in both domains. So this is really nice. Like your slice can still extend through the two domains end-to-end while using MPLS in the rest of the network and using SRv6 in your edge data center. So my colleague Jorge has a presentation, I think at 5 p.m., where he goes into more details about these use cases. The other use case I thought of was if you're doing a network core migration from, say, IPv4 OSPF v2 to IPv6 ISIS, you can still do that migration node by node in the sense that you can deploy, obviously, your P routers that are SRv6 capable, and then you keep your existing MPLS routers. And then you go PE by PE and you start your upgrades. And a router that does only MPLS will advertise routes that are only traditional MPLS with a service label, and that's fine. But if you upgrade these routers with SRv6 and you use this interworking gateway, then you have both SRv6 and MPLS instances in that VRF, for example, or EVPN instance. And what that allows you to do is you can actually advertise two routes, one with a service label for MPLS and one for SRv6 with a service SID, like shown here. And on the receive side, an upgraded router will obviously do the best path selection. And if there's a tie, you can always favor SRv6 over MPLS, so you can resolve it to the SRv6. If there's failure in the SRv6, you can do edge pick and fallback to the MPLS route. So that gives you really a nice failover. For the nodes that are not upgradable or are not upgraded, then obviously they can only resolve to the SRO-SPF tunnel in MPLS. And basically over time, the routers get upgraded to support SRv6. And at some point in time, MPLS will be obviously discontinued in this network, and you don't need to do any more of the gateway. But you know that typically the way this migration happens is you do a dual plane. It takes years before the transition is over. So you can still operate the network like that and still have a nice behavior, fallback, and no issues here. That's actually my last slide. So I don't know if we have time, Bruno, for questions. 1.
Thank you very much, Mustapha.